Okay, we are live. Everyone check out, so I realized that there's two ways we could do this. So I'm going to post the videos on Blackboard because I guess that's where you post things for class. But then I think it's so much easier to access just if I put it on YouTube. And so I'm going to do that too. Don't downvote it on YouTube, right? 'Cause you're going to kill my karma or whatever you get for YouTube. All right. So I told you a story last class about how we're trashy people, and my wife thought we had a bush in our front yard that was actually just our discarded Christmas tree.
It does look like a bush.
So there it is.
Oh my. It does look like a bush. I can see what she would have thought.
Maybe you should put a bush there.
It's a nice spot for a bush. Maybe we'll leave it. Also, I love about this picture because if you look closely, look who's right there.
Oh, there it is.
Just watching. All right, so I used to love grading until this weekend. Oh my God. So, assuming that I give everyone's exam a total of 5 minutes, 300 times 5 is a lot of minutes. I'm not done grading yet. Trust me, I've spent a significant amount of time. I've basically got just the last page to grade, and so my goal is to go home right after class, put on some movies, and do that last page, or else I'm going to go out of my mind. So, yeah, hopefully I'll have exams back by Wednesday, and then we don't have anything to do in this class until like the Friday after spring break. So yeah, I got an email, a panicked email asking me if one of your classmates could have an extension on the homework that was due on Friday. Which of course there was no homework due, so don't relax if you didn't get that in. And so, interestingly enough, I was reading The Economist this weekend. I was actually reading about tariffs in India, because that's what you do when you get older, is you read articles on Indian tariffs in The Economist. Anyway, I was browsing through this article, and it mentioned that the tariffs are so high on imported alcohol in India that a lot of alcohol is homemade in India. And so that can be more dangerous because there's not really quality controls. And so last year, and this isn't funny, but last year I told you about methanol, how that can kind of sneak into booze if things aren't done correctly. And so supposedly last year, 1,700 Indians died just because of methanol-laced booze, right, that they had made. So it's a significant issue, and that's why we have things like quality controls on as much as possible. Okay, so I showed my wife my podcast, and she was like, "Why do you do like a monologue at the beginning?" And I was like, "I don't know. It's finally my chance to be a talk show host or something." So. It's my stand-up gig. All right, so stereochemistry. Our theme song today was one of my favorite songs, "Complicated" by Avril Lavigne. And so we're going to see, we're hopefully by the end of the class not going to think that this stuff is complicated, because we're going to try to make it as simple as possible. And so last time what we did, we talked about how we can name stereocenters with either R and S, and we learned 2 ways to do it. The easiest of which, in my opinion, is basically the thumb rule, right? So you align your thumb with the 4th component, or the 4th priority substituent, and then whichever way wraps, if it's your right hand, it'd be the R stereocenter. If it was your left hand, it would be the S stereocenter. So pretty easy to remember. I just wanted to maybe do a few examples of naming stereocenters today. So let's see. We could have this molecule. We'll put a bromine on the dash, and then a hydrogen on a wedge. And so anytime you see, well, first off, we ask ourselves the question, is this carbon bonded to 4 different groups? It most certainly is. And so when we look at this, we know that there's a stereocenter because of that. And so we need to prioritize the groups. Now we have a hydrogen, and we always know if there's a hydrogen that it's going to have what priority? 4. It's always going to be priority 4. So we can go ahead and just call that 4. What's going to be number 1? certainly the bromine, just because of atomic weight, right? So it's heavier than carbons. And then we have a methyl and an ethyl, and so what's going to be a higher priority?
Ethyl.
Certainly the ethyl. And so what we've got is 1, 2, 3, 4. And so what we want to be able to do is, if we want to use the thumb rule, what we could say is, well, if we aligned our thumb with our wedge, and so it's kind of going this way, are we going to wrap 1, 2, 3 correctly? Yeah, so if where my fingers are 1, and we continue to wrap, that's going to get to 2, and then on up to 3, right? And so that would be perfectly fine. So in this case, we've got the R stereo center. Let's see what happens if we try our left hand. So we align our thumb. We start our fingers at 1, but what's the next number it encounters? It would be 3, and so that's no good. And so this can help you because your hydrogen's not always going to be going back in the board. It can be going this way, but the rule stands because you can orient your hand whichever way that your molecule is oriented. So that makes it pretty easy. Okay, furthermore, if you kind of, if you wanted to just do this visually, which you can certainly do, you could say, well, I could imagine my eye is going to hide the hydrogen, and so our eye would kind of be back behind the molecule. And so if that's the case, if we were looking from behind this molecule, would we be counting 1, 2, 3 clockwise or counterclockwise? So it looks counterclockwise from the front of the molecule, but it'd be clockwise if we were from the back looking at it, right? Because we've changed our perspective. We're looking on the opposite side of substituent of the fourth substituent, which is on the front. So that puts us on the back, and so it's actually clockwise. And so we've got R. Makes sense. Okay. And so we can also name this molecule. And that's what I'm going to start doing. I'm going to start throwing some naming in because I told you that I wasn't too worried about naming for the first exam. But as we go, I just want to kind of organically learn some naming techniques. And so what would be the longest carbon chain in this case? Yeah, it's just one carbon chain, right? And so there's 4 carbons, so we've got our ethyl group down here, so 1, 2, 3, and then 4, and so we're going to give this molecule what kind of root? Yeah, it's going to be butane. And so furthermore, what we would say is that, well, we have a substituent, and so what we can do is we can number 1, 2, 3, 4, because our only substituent is that bromine, and so we want to give bromine the lowest number. And how are we going to designate a bromine substituent? Bromo, right? And so we would say that this is 2-bromobutane, and that's our name. So just like we would say 2-ethyl butane, we'd say that, like something like 2-methylbutane, we would say 2-bromobutane as well. So how do we indicate the stereo center? What you do is at the beginning, you just say it's R, right? So that's because when we named this stereo center, we figured out that it had the orientation of R. What? Oh, whoops. Why is it? I don't know, that's not my fault. What's going on there? It's like, let me just move it. I'll have to tell them that that's not right. Let's see, I can copy and paste this over. Okay, yeah, sorry about that. I'll let IT know. I guess it's their job. Okay, so this is basically how it's going to go, where you're going to be given a molecule, you're going to want to be able to locate the stereo center, and then once it's located, you'll have to give a designation. How many possible molecules are there with the connectivity of 2-bromobutane? Should be 2, right? So we have R2-bromobutane. We could also have S2-bromobutane. All right, so a couple of possibilities. And the relationship between those 2 molecules is that they would be enantiomers. Yep, Gabby?
How did you get the bromo?
So that's just from our bromine substituent. So what I'm going to do is as we write down molecules, I'm just going to start introducing names to that. So whenever you see a halogen, you're just going to say it's a substituent. We start out with the first part of that halogen. So you have 2-chloro, 2-bromo, 2-iodo, 2-fluoro, just like that. Yeah. Okay. Let's look at another example. All right, so this molecule, first off, we want to think, is there a chiral center in this molecule? Do we have a carbon bonded to 4 different things? So we might think that this is a chiral center, but what's going to happen is if we count down 1, 2, 3, and then count down 1, 2, 3, are those groups different? They are in fact not different, right? And so do we actually have a chiral center? We do not. So in this case, there is no chiral center, and so if there's no chiral center, there's not going to be any RS designation. We've got to be bonded to 4 different groups, so that includes rings. If it's connected to a ring like this, and when we count down the ring, and we find it's the same thing, then we can't assign one of those directions a higher priority, and so we know that it's not a chiral center. What we could do is we could change this to look like this. And so now when we count down the ring, do we have the same, no, we don't. So in this case, let's see. So we have a hydrogen on this chiral center. So what do we know that priority is? Definitely 4. Makes it nice and easy. And so of the other 3 substituents, basically what we've got is we've got a carbon here, here, and here. And so that's all carbon, so that doesn't give us any help. So we count to the, we look for the first point of difference. And so, well, this carbon's got an oxygen bonded to it, whereas this one and this one both have just carbons and hydrogens. And so that tells us that this direction is going to be which priority? Yeah, it's going to be 1. And again, it's because of that second point of difference. So the first point is just carbons, and so the next best thing we've got are yeah, Josh?
So the reason we give carbon 2 on the left side priority 1 is so that oxygen has the lowest number.
It's because since this, and this are all carbons, we look for then the carbon that has the highest attached atomic number, right? And so oxygen's higher than carbon or hydrogen, which is the only other options here and here, and so we give that priority 1. Yeah. All right, then. So we've got the ring here, and so this, of course, has a couple of hydrogens off of it, and then we have this carbon. Now, this carbon we assume, or we treat it as being connected to how many carbons? 3, right? So 1 here, and then it's bonded to this one twice, and so we see that's a total of 3 carbons. How many carbons is this connected to? 1, and so what's the higher priority? It's the top one, right? It's the one with more carbons, and so we call this number 2. We call this number 3. All right, so then we can basically do the same thing. So we've got our hydrogen in front. So if we put our thumb towards us and we wrap with our right hand, does that count 1, 2, 3? No, but if we do our left hand, thumb towards us, and we do that, does that count 1, 2, 3? It does. And so that means that it is what kind of stereocenter? S. All right. So you're going to want to have a handle on that. Basically be able to look at a molecule, point out the chiral centers, and then figure out if it is R or it is S using that process that we just used. Okay. So just a drawing technique is I want to say that there are 2 different ways to draw enantiomers. And so above we have R2-bromobutane. What I want to do is basically, well, the harder way in my opinion is to do the mirror plane. And so that requires you to change the orientation of everything. So if we're going to do the mirror plane, and for this case we're going to draw S2-bromobutane. All right, so number 1 is what we do with the mirror plane. So we imagine what it would look like as a mirror image. And so in that case, we've got our methyl group up. Our ethyl is now this direction. Our bromine is to the back on the opposite side. And then our hydrogen is to the front on the opposite side. So does everyone see how we basically took the mirror image of R-bromobutane to come up with S-bromobutane? Yeah, okay, so this is S if we undergo the same process. The other way that we can do it, and the way that probably is more common and is definitely easier, is you just swap 2 groups and then leave 2 the same. And so what we can do, all right, so we've got, we can basically just copy everything down, say on the lines, and so we'd say CH2, CH3 in the same orientation, and we're just going to swap our bromine and our hydrogen. So the bromine that was on a dash is now on what? Now on a wedge. And the hydrogen that was on a wedge is now on a dash, right? And so there's two ways you can go about this, and honestly I think this one is easier because you have the same thing, you just switch two of the groups, and you have the other enantiomer. So in both cases we have S, and I just want everyone to be aware that you'll probably in your lives at some point see this done both ways. Okay, so that's how we draw enantiomers. Next up is going to be section 4. So section 4, we're going to refer to Fisher projections, which honestly, I don't like Fisher projections that much, but other people here teach them, and so we're at least going to go see what they are and then probably not use them as much as others do. I think they're honestly a little more confusing. Okay, so what Fisher projections do is they orient our structure so that vertical substituents project away from you, and then horizontal substituents project towards you. Okay, so this is typically, you'll often see carbohydrates drawn this way, and it's because carbohydrates have a pretty high degree of chiral centers in them, and so there's a lot of stereo information to get across. Yes, Sam?
Sorry, just going back to the example of swapping them.
Mm-hmm.
When you swapped the hydrogen and the bromine, it was still the S enantiomer, so you ended up drawing the same one. Like, why is it still the S?
Why are these both S?
Yeah.
Well, because we can draw that. Basically, I was showing that you can go from R to S in two different ways. You can draw the mirror plane, right, where everything is just like a mirror image would be, or you can just swap these two groups.
Oh, so those two enantiomers are the same, but that S is different than the R that's up there.
Right, and so these two things are the same thing. And you should be able to see that. So if we imagine taking this and we rotated this 180 degrees, this bromine that was in the back is going to rotate all the way around to the front and then be on a wedge, right? And that's exactly what we've got here. Yeah, so those are the same exact molecules. Those are both S. I've just shown two different ways to go from R to S. All right, so our Fisher projections, and typically by convention, what is done is the carbon with the most CO double bonds is placed on top, and that's just a carbohydrate thing. So typically how you'll see these things drawn. So first off, if we reorient our molecule, so let's say we've got a carboxylic acid functional group on top. All right, so this is more or less just a 3D picture of our thing, right? And so what we want to do is we want to rotate this. So this bottom thing, we want to rotate a little bit so that ultimately what we have is this picture. So the vertical substituents are projecting away. So our methyl group has been rotated. It's still in front. Our hydroxyl group has been rotated so that it's now on a wedge. And then our hydrogen's back on a dash. And so we should be able to see how we basically rotated those bottom three substituents a little bit to get this picture right here. And so ultimately, you don't have to keep the wedge and the dash. And so what you end up with is a picture that you can just draw single lines on like that. And so what this does is it's another way that we can basically get stereochemistry. It's used with carbohydrates. I'll show an example of that. There's an easy way to remember which lines are coming towards you and which lines are coming away from you. And so honest to God, when I took this class 10 years ago, this is the teaching tool I remembered from that long ago. So you'll probably remember it too. Whenever you have a Fisher projection, what you imagine is you yourself, you're in a field, and you haven't seen someone for a really long time. but you're so happy. There they are. They are here in front of you. And so your first result is just to run towards them. And so you run out with your arms stretched. And so these horizontal things, they are going towards your friend, but you're so carried away that your feet are behind you and so are your head. So that's how you remember the Fisher projection. You just can't wait to see this person. So there you are, just like that. Okay, so I remember that for a decade, and I doubt you'll forget it. So that's how we remember. Okay. That said, I really don't like Fisher projections. Okay, so just an example. Like I said, a lot of carbohydrates, and so in the lab manual, there's a lab at some point that depicts carbohydrates this way, and so just so we can see what it is. Is this too far to the left? Let's all right, so we've got D-glucose, and so on a Fisher projection, what D-glucose is going to look like is basically. So we have our carboxylic acid up top, and that's just because by convention, the C double bonded to an O goes on top. And so we have hydroxyl groups coming off of carbons. And so whenever you have the open chain form of glucose, it'll be drawn like that. And so what we've got is we've got stereosymbol there, 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 and there. All right. But like I said, we're not even going to worry about naming these because I don't like them. And so what do you think the likelihood of me giving you this picture on an exam and saying, what is this RS? How likely is that? It's so zero that I can't even, it is zero. So I just want you to have seen this because going forward you might. And so what this ultimately is when it wraps back around into its cyclic form, which is thermodynamically favored. If you ever just want to talk about sugars, it was my PhD research. So if you're ever bored. If we draw this out in the cyclic form, what you have is these stereocenters that look like this, and so let's actually number these. Let's say that we've got carbons 1, 2, 3, 4, 5, 6, and so what happens is we have the oxygen here, really. We'll name this 7. It wraps around, and so what you end up with is this. All right, so basically this is really an equilibrium. So sugars, it's an equilibrium. They can be open or they can be cyclic. And so it turns out that the cyclic form is like 99.99% favored. Why would it be? Why do you think this is pretty favorable? It's a 6-membered ring. How stable are those things? They're very stable. And so it's just a very thermodynamically stable way for things to exist. So most of the glucose that exists is existing like that. And then ultimately, what we can do is we can show this in a chair. And so we'd say glucose looks like this. Notice that when we draw this chair out, those hydroxyl groups, are they axial or equatorial? They're equatorial. That's why glucose is so friggin' stable, right? It's because when we draw it out in this chair form, everything's equatorial, and so it's an even more stable way to have our chair form exist. So glucose, a very stable molecule. I think that's about as far as we're going to go with Fisher projections. By the way, grading, yeah, Rhea?
Can you explain why the things that you starred are stereochemical?
Because they're bonded to 4 different groups, right? They're carbons that are bound to 4 different things. So, for example, here, this carbon on the left is a hydrogen, here it's a hydroxyl group, here's the CH2OH, and then up top is all that next one, so 4 different things. Yeah. And so each one of those is bonded to 4 different things. So that's why it's a stereocenter. Yeah. By the way, on the exam, I asked you to explain something in 10 words or less. And so there were a number of people that used like 6-point font and wrote like 120 words. I didn't take off for that. But going forward, if I say 10 words or less, let's keep it to 10 words or less. A one-word answer would have gotten you full credit on that, so definitely don't overthink it. Okay.
I've not used symbols to get around the word. Oh my god. And I was like, well, if I say A, it's not really a word, but it wants to describe what I know.
Oh, don't you dare bullshit like that. Don't you dare bullshit like that.
All right, we're good?
It was a letter.
A is totally a word.
It's just B, a word?
Okay, so next up is Roman numeral number 5. And so that's going to be relationships between stereoisomers. And we've already talked about a really special relationship, right? Enantiomers. They are a very special pair. That's how you're going to remember enantiomers. There's always 2 of them. There are a pair of enantiomers always. So let's just get back down on paper a few things. So let's just redefine stereoisomers. And so stereoisomers, as we've seen, are always just going to be molecules with the same connectivity, but different orientation. And so we're certainly going to have cases, as we've seen with the glucose, where, well, sometimes you can have multiple stereocenters in one molecule, right? So that quickly breeds complexity in our molecule because the number of stereoisomers ultimately grows exponentially. All right, so what we can say is that for a given molecule, the max number of stereoisomers is going to be equal to 2 to the n, where n equals the number of RS or EZ stereosites. All right, so it's not too bad if we've got 1, it's not too bad if we've got 2, but in something like carbohydrates, we can have 5. How many possible stereoisomers are there? 32, and so that's why you've got so many different kinds of sugars, right? Glucose, mannose, galactose, all these sugars, they have the same connectivity. We just are talking about stereoisomers. So those hydroxyl groups have a different orientation, and that's what makes them different, yeah?
So will a set of stereoisomers have the same number of RS and EZ types?
Say that again?
So will a stereoisomer have, will like a molecule have the same number of RS configurations and EZ configurations?
Yeah, I mean, so stereoisomers have the same chiral centers, right, or the same stereosites, yeah, definitely. All right, so what we can do is we can say there's going to be a certain number of stereocenters, and then we've learned about our special pair, and so we define that as enantiomers. And so I will continue that use of special pair because you're not going to forget it. You're not going to forget what an enantiomer is if you remember that. So it's a special pair, and so that special pair are non-identical mirror images, or you could say non-superimposable mirror images. And so, for example, we're going to start looking at molecules, and we're going to look at molecules that have multiple stereocenters, and we want to figure out if they're enantiomers or if they're not enantiomers, and if they're not enantiomers, what do we call them, basically. And so the first thing we'll look at, so let's look at this molecule. All right, so let's see, let's put a bromine here, hydrogen here, and then we'll put a double bond there. Okay, so what we want to be able to do is look at that, and we want to determine the labels for those stereosites. And so we've got a double bond, and so we could use cis or trans here, but I'd prefer we use E and Z because E and Z are always applicable. And so if we were to give this double bond a designation, would we call it Z or would we call it E? So the groups are on opposite sides. So unlike the letter E, where they are on the same side, it's an E, right? Worst tool to remember that by in the world. All right, so our groups, and remember, of course, if you couldn't remember how this is done, those are just hydrogens there, right? And so hydrogens are always lowest priority, so our high priority groups are the carbons, they're on opposite sides, and so we use E anytime we have groups on opposite sides like that. So then we get to our stereo center, and so we know automatically that our hydrogen's going to be number 4, our bromine's going to be number 1, and so then we have to name, basically figure out the carbon chain. Is that 2 or 3? So here we've got a CH3, here we've got a carbon connected. We would consider it connected to how many carbons? 2. And so this carbon or this carbon is going to be higher priority. Should be the top one, right? Because it's connected to 2 carbons, and carbons are heavier than hydrogen. So we've got 2 here and 3 here. Okay, so again, we can use our thumb rule. So we see that our hydrogen's coming towards us, and if we point it that way and we curl our right hand, can we go 1, 2, 3? We can, right? And so that's going to be R. All right, so we've looked at our molecule, and we've seen that it is E and R. All right, and so what we can do is we can say, well, we know, of course, that we can find the mirror image of that, right? And so if we find the mirror image of that, of course, what's the relationship going to be? Enantiomers. Are enantiomers stereoisomers? Yeah, so basically, enantiomer falls under the class of stereoisomers, right? So we have a set that we call stereoisomers, and then we have a subset of enantiomers, and we're going to find that we have another subset when things aren't mirror images. But in this case, we are enantiomers, and so when we take the mirror image of this, what we end up with is this picture. All right, now this is a really key important point. There's a reason I'm doing this example. Now, we've taken the mirror image of an R chiral center, which means that the chiral center of the enantiomer is going to be what? It's most definitely going to be S. Anytime we take the mirror image of a chiral center, it's going to switch to the other possible naming designation. However, that double bond, has it become a Z double bond? It has not. And so what we find is that when we're talking about enantiomers, the chiral centers that we name R or S definitely do change, but the E or Z that names the double bond does not change, right? And we can see why that is. It's just the mirror image, all right? And so the 2 groups in that double bond, they haven't changed their orientation in the mirror plane. All right, so we definitely want to make sure that as we go forward, we will say that enantiomers have the same EZ orientation, but they have different, or the opposite, RS orientation. All right. And there's proof of that on the left. So let's see. So when we're naming stereo, the max number of stereo sites, we're not worried about just chiral centers, we're worried about double bonds as well. And so how many possible stereo sites do we have in this molecule? How many times do we name a stereo site with a letter? 2, right? So we're calling it R, and then we're calling them E. And so what we want to say is that the max number of stereoisomers is going to be equal to 2 to the n, and so our n here is 2, and so we're going to have 4 possible, or at least 4 max, let's say 4 possible. We're going to have 4 possible stereoisomers here. So what we can do is we can just pretty much draw them. So let's say that we have, let's just copy these 2 down. So we've got this molecule that we will call ER. So we'll label this letter A. And then we had that mirror image, and so we know the mirror image was this. And so we also know that this was what we will call ES. We'll label that letter B. But we've got 2 more possible. That's just 2 of the 4 total stereoisomers that are going to be possible since we have 2 sites. And so we've used ER, we've used ES, and so what have we not been using? We haven't been using Z, right? And so what we're going to have is, let's see, we would have ZR and then ZS. And so what would that look like? So ZR will draw on the same orientation for our R. And so we know that's the R stereosite, because if it in this orientation, if this was R, I need to put that hydrogen on a wedge, then this is going to be R as well. But what's changed is that double bond, and so we'll change it like that. And so we end up with is the Z there. And so of course, these are mirror images. We can take the mirror image of that. What we end up with is that picture. Okay, so that should be 4 different molecules. Are these enantiomers? These are enantiomers, right? Because we've got the mirror images. We see that our R has changed to our S, but our Z has stayed the same. And so now what we've got up here are 4 possible stereoisomers. We knew that we had a max possible number of them of 4. And so what we want to talk about is the relationship between these things. So what I'm going to do, I think the easiest way to say this is we'll say that we've got, A, B, C, and D. Okay. So we've said that the relationship, they're all stereoisomers of each other because they have the same connectivity. The relationship between A and B is what? What would we call that special pair? They're enantiomers, and so I'm going to put an E there. Stands for enantiomers. All right, so then C and D, what is that relationship? Also enantiomers. It's a special pair. There's always 2 of them when we talk about enantiomers. But all of these things, for example, A and C, does that qualify as a stereoisomer of each other? It should, right? And so what we're going to do is we're going to give this a special name. What is that name? Diastereomer, and we're going to use a D. And so quickly what we want to do is these names sound confusing, but they're not. So let's define this in the easiest way possible. Let's say that a diastereomer is going to be any stereoisomer that is not an enantiomer. How easy is that? If it's not an enantiomer, if they are not mirror images, that means they must be diastereomers. It's that simple. It really isn't that complicated. And so A and C, they're diastereomers. What about B and D? They're diastereomers. What about C and B? They're diastereomers. What about A and D? They're diastereomers. And so what we have are lots of pairs of diastereomers, but they're not a special pair, right? Special pairs are the enantiomers that are mirror images. Okay. So the point of this Roman numeral is basically to look at all these different possibilities, relationships between stereoisomers, and be able to point at them and say, well, those are enantiomers, or those are diastereomers. Let's do another example. Alright, so we'll have put a hydroxyl group here, methyl group, bromine, and then we'll go with another methyl group. Okay. So certainly we could look at this and we could say, well, these, we could say that hydroxyl is higher priority here, and then bromine is higher priority there, and we could name it cis or trans, but what we're going to find is that each of these is actually a stereocenter. It's actually a chiral center, and so cis and trans doesn't give us enough information, because ultimately, how many possible stereoisomers will there be? 2 to the 2, right? There should be 4. If there's 2 stereosites, there should be 4 possible stereoisomers. So cis-trans doesn't cut it here. So what we'd say is we would label this, of course, priority number 1. We'd name the methyl priority 4, and this would be 2 and 3. And so at this point, we should be catching on. The reason for that is obviously oxygen is higher atomic mass, and then this is a CH2 bound to something with the bromine, and this is a CH2 just bound to more CH2s, and so that's going to mean this is higher priority than this one, and then finally, that's just a CH3, so it gets 4th place. And so what we end up with is this stereo center is an R, and so we should be able to see that if we put the group of priority 4 in the back. We're going to count 1, 2, 3, and we should be able to wrap 1, 2, 3 with our right hand, and so it is in fact R. And so the other one we will do similarly. So we've got priority 1, 2, 3, 4. And so in this case, we want to wrap 1, 2, 3, and again our methyl's coming towards us, and so we would wrap 1, 2, 3 like that with our right hand. And so yet again, we have an R stereo center. Okay, so we've got R and R. And so what we're going to have is, of course, we have R and R. If we want to talk about the enantiomer, well, we don't even need to draw it out anymore. We should know immediately what the enantiomer's chiral designations will be. Yeah, so it should be S and S, because we've already learned that an enantiomer always has the opposite chiral designation, and so we'd say the enantiomer is going to be S and S. Likewise, we could have R and S down here, or S and R, and again, the relationship here is that they are what? Yeah, and so whenever we have our special pair and we have nothing but chiral centers, we find that the letters are just opposite, right? So if we had R, 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 what would the enantiomer be? It'd be SSS. It's just that special pair where everything is opposite. What if we had RSR? What would the enantiomer be? SRS, just like that. All right, so then of course that doesn't talk about all the other possible relationships. So RR and RS, are those opposite? One of them is, but one of them isn't, and since one of them isn't, we know they can't be enantiomers, and so they must be diastereomers, right? So we pretty much end up with the same picture as we did before. Key point being is we want to remember that enantiomers have the same EZ designation, right? The double bond designation does not flip. All right, so what we can say about this is that if all chiral centers are flipped, then we're talking about enantiomers. And basically all other possible stereoisomers are going to be diastereomers. All right. Okay, so we have 5 minutes. Let's move into the next Roman numeral really quickly. So we'll call this number 6. And so we've been talking about chiral centers, but now we're going to start trying to think about the big overarching picture of chirality. And so instead of just looking at individual stereosites, we want to start talking about chiral molecules. And ultimately, an important idea behind this is going to be the symmetry that we see in molecules. Because there is one special note that doesn't fall under the name of enantiomers or diastereomers. Okay, so let's say that, by definition, chiral molecules have a non-identical mirror image. And this is going to be important because what we're going to find is that sometimes there are going to be cases where we have a chiral center, but we don't actually have a chiral molecule. And so to help answer that question, if I pointed out a molecule to you and I said, is this a chiral molecule? We would use this definition. We would say that chiral molecules always by definition have an enantiomer. So what that means is that we might start finding a few cases where we find chiral centers in a molecule, but the molecule, when we try to make an enantiomer, we find is actually the same molecule. All right, so that's kind of the theme of Roman numeral 6. Not only do we want to find chiral centers, but we also want to talk about molecules. Are they chiral or are they not? So we'll ask ourselves a question. The question will be, is a molecule with chiral centers always chiral itself? So the answer to that question is no. All right. We've got 3 minutes. This probably isn't the topic to try to squeeze into 3 minutes. So we'll lead with this next time. And honestly, we may be able to finish stereochemistry on Wednesday. So yeah, we're making a good time. Oh, by the way, so I haven't been particularly satisfied with the textbook in terms of problems I can give for you, additional problems. And so I actually have won a grant to start developing an open source organic chemistry workbook. And so I figure I can probably kill 2 birds with 1 stone by making my own problems for you, as well as start using those problems in that workbook. And so the reason I haven't posted any homework problems yet is because that's what I'm going to be doing. Those will be coming as soon as possible.
You know that's one. Have a good day.
You too. Let's see. Anything about who to talk to in that case? What are you interested in? So I was like, in your question? Okay. Send me an email.